session.
All right, so today's session will be about AMD ROCm support in EESSI, and it will be presented by Ayush. Ayush is a master student who's done his internship at SURF in the Netherlands, and his main theme of the internship was basically to get this thing working in EESSI. Ayush, wait, there's a second slide that I should probably say something about, which is the highlights. So, just to make you aware, there's an ISC conference in Hamburg 2022 to 2026, where several people from the EESSI consortium are present, I think. So if you want to meet up, that's one opportunity. And another one will be at the Euro HPC User Days. I don't think we have Kenneth with us, but he was thinking about doing some hackathon there as well on EESSI. That is not yet confirmed, but keep an eye out for that if you're interested. All
Uh,
right.
Before
With that,
going to Ayush, just a reminder that the session is being recorded, and at the end of the session, we will stop the recording for informal conversation. So, and yes, Ayush, the session is yours.
Okay. Um, Hello everyone, welcome. So today we are going to talk about how we implemented the AMD ROCm support. Uh, I'll go over the current scenario. So Easy currently supports CUDA and the entire software stack is shipped and it works with host injections. So the problem is that CUDA is not redistributable and the compiler and runtime are supposed to be present on the host system, which would be symlinked to the easy software that is provided. The An important part of CUDA is also that the softwares are actually built as PTX fat binaries, and the code generation is actually deferred to the system driver. The interesting part is that ROCm support is now necessary as more HPC systems are coming up with AMD GPUs. For example, Lumi is already available, and Jupyter is coming up, which is supposed to have AMD GPUs as well. Um, so the main differences between ROCm and CUDA, and this also defines the entire work done in this project because ROCm is actually available as Apache with MIT and Apache licenses. And this means that it is completely redistributable, no need of symlinking the compiler and runtime, everything can be shipped. Uh, the interesting part is that there is no PTX equivalent mechanism here. So for every GFX target of the AMD GPUs, we need to build software for each GFX targets. This also means that there is a very high coupling between the libraries provided and the compilers and drivers. Uh, the good part is that actually the bad part is that there is only 1 year of guaranteed support between the ROCm versions and the driver versions. So we need to place a hard minimum version requirement on the drivers available on site. Uh, so now I'll go over how the ROCm 6.4.1 stack was built. So using the GCC core 14.2, we were able to build ROCm LLVM, which is supposed to be the base of all the packages which will be developed in the future of this work. Using the ROCm LLVM, we are able to create a ROCm compilers toolchain, and a separate easy block was created known as ROCm component. And using both of these, we'll be able to develop all the packages supplied with ROCm 6.4.1. So, for example, HipBlast, RockBlast, Rickle, Rock50, everything was built and merged into the easyconfigs repository. We decided that ROCm 6.4.1 will be available for all the GFX targets it supports. So for it is available for 1030, 1100, and so on and so forth. So regarding what GPUs can be supported, a few examples would be MI210, MI250X and MI300X as well. Uh, Now, how this makes our life a bit difficult using EasyBuild is that when AMD software stack is provided using a vendor, it actually installs everything in a path called /opt/ROCm, and this is the standard installation available everywhere. Now, with EasyBuild, as we all know, that we install each package into their own separate library, and their paths are mm, published as EB root environment variables. Now, majority of the patches that were needed to build these libraries were uh, supposed to remove this hard coding. So all the CMake uh, installation scripts actually expect the heap ROCm LLVM and ROCblast, all the dependencies to be available inside one installation. So we had to point these to easy build packages separately. Uh, this is a screenshot of all the packages that were merged. There were around 30 or 40 packages that were merged with this pull request, and the link is available here for you to check later. This basically covers the entire stack without touching the MPI part. Now, the next phase would be to actually build the open MPI toolchains known as ROMPI, and this is analogous to the NVIDIA open MPI toolchains known as GOMPI and others. So the ROCm uh, the ROCm driver, the ROCm packages actually. So we'll go over each of the package that enables us to use the ROCm drivers. So one of them is swlog, which enables packages to search for the ROCm topologies available on your system. Then UCC is also built specifically for ROCm drivers, similar for UCX and XPMM. XPMM is used to access the Infinity Fabric available on the ROCm, uh, on the MI250 GPUs. Now, using all of these were supplied to OpenMPI, and thus the OpenMPI package is now configured to access all the transfer mechanisms available on AMD GPUs. Using this OpenAPI and the ROCm compilers toolchain, we built the Rombi toolchain, and based on which we were able to build the OSU micro benchmarks as a sample application. Now, another toolchain that is important to us is the RFOS toolchain, which is similar to the LFOS toolchain available. And it is built on top of the Rompi toolchain. The additions being FFTW, ScalaPack, FlexiBlast, all the FOSS libraries um, are supplied to this RFOS toolchain, and GROMAX was another application which was built to demonstrate that all of this works. Now moving on to the performance part of how this performs to the actual native vendor installations. We want our easy installations to work close to what the vendor systems actually provide. Now, this toolchains work nicely for intra-node jobs and single node jobs that you might be able to run. The exceptions are for small message sizes and internode communication on Slingshot 11 cannot be enabled nicely since we expect that there are uh, hardware optimizations done on Lumi in collaboration with AMD for all the small message transports. So the cost of establishing a network is actually uh, optimized nicely. OpenMPI built with UCX cannot access those hardware optimizations, and thus the performance you can see that EC was actually 500% slower or 300% slower compared to the native installations. Now, another part is that OpenMPI 5.0.7 exports libmpi.so.40, which is not compatible with the MPitch ABI family that is expecting libmpi.so.12. Now, we tried to do a host injection on OpenMPI. So we basically took the OpenMPI and tried to inject the MPI libraries available on the system, but this did not work because of this incompatibility. And thus, the transfers on internode were falling back to the primitive TCP transfer mechanisms. In this graph, you can see we tried to do a collective benchmarks with OSU, and you can actually see that EC is easily an order or more slower compared to the native installations. So the solution was to actually use an MPitch toolchain altogether. We let go of the OpenMPI and we took a different path of building MPitch 4.3.2 with the ROCm compilers toolchain. Now, using this MPitch 4.3.2, we were able to build an RMPitch toolchain, which is similar to ROMPI, but uses the MPitch mechanism. The good part is it will now export the libmpi.so.12, and we can actually link this against the vendor MPI installations. So once these OSU, when we try to build OSU and GROMAX, once the installations are successful, we strip off the easy build MPitch installations from the DTR path. So the LD library path override can work later on. Now, once these were built and before running the application, we add the /opt/cray MPI libs to the LD library path. And the good part is it is able to access the vendor MPI installations. And the performance of Easy is now very similar to the vendor installations. Now, I have some code snippets which will show you what change happens when we do this interchange. So before you can see that libmpi.so.12 was being linked to the CVMFS MPitch installations. And once we switch the LD library path, these are now pointing to the /opt/cray installations. And the results are pretty nice. For EC, you can see the blue bars, and for the native installation, you can see the red parts. So you can see that for all the collective benchmarks on internode systems, EC and the native installations are very similar, almost neck to neck on all the installations. And this is expected since we are actually using the same transfer mechanisms. So this proves that we can uh, change the MPI transport mechanisms on the go. And this can be useful for all systems using Slingshot 11. We haven't tested this on systems using InfinityBand or some other transfer mechanisms. My guess is that we won't have to use MPitch, uh, MPitch toolchains and libraries, and the host injection can just work on OpenMPI itself. Also, we tried benchmarking GROMAX, and for the large data sets, which is the second and the third one, the performance is quite similar for easy installations and the native versions. For those of you looking keenly, uh, the performance of easy systems is actually better than the native systems. And we attribute this increase in performance to the difference in the ROCm versions on the two systems. So with Easy, we are providing ROCm 6.4.1, and on the native on Lumi system, we have 6.3.4 as of now. So we are attributing this increasing performance to those version differences. And other than that, everything seems to work nicely. Now, this solution that we did of stripping off the DTR path and manually loading these libraries to LD library path was actually a hack to in, uh, was a hack, so we don't have to use the host injection solution for now. Once we have the host injection solution in place, we need to point Tosu and Gromax and other applications to a placeholder path in the CVMFS repository. And there would be a script which would have to be built that would link those placeholder paths to /opt-cray MPI loops. And we would need to work with Lumi and other systems so the sysadmins can actually run these scripts and do the correct symlinking. But this work actually proves that this is possible and we could bring the easy performance to parity with native. This has also been a joint effort between multiple people and organizations. And the base for this work was actually built by Kenneth, Jan Andre, Bob Droger, Casper, and the ROCm LLVM easy block, easy config, ROCm component easy block, and the ROCm compiler's toolchain was provided, on top of which we were able to build all the other easy configs. And the work for ROCm 7.2 and the ROC is currently ongoing. So we'll see that later. The reason for choosing ROCm 6.4.1 was actually that this stack, as of now, is stable and no more changes are being done. AMD is very quick in making changes, and that doesn't allow us to use a stable system to work with. But 6.4.1 was already stable and there was already some work done. So we decided to publish this version for now. Once the easy configs are merged and available in easy, this you can, I'm sorry. Yes, once these are available on easy, you will just be able to pull them simply on your system if you have an AMD GPU and work with it. Yes, that is that's it from my side.
All right, thank you very much, Ayush. I guess that kind of expands the whole AMD support thing to also cover the interconnect on Lumi. I think that makes sense, right? Like, I mean, it is one of the big AMD systems that are out there in the wild right now. Maybe it's good to add that the whole host injection thing is not necessary for AMD systems in general, right? It depends on the interconnect. So yeah, it adds extra complexity if you have this interconnect, but at least there's knobs that you can turn to actually then use the host MPI to get the native performance on those types of systems. Regarding the AMD support in general, I think you also had, I don't know if you had that in this slide deck, but you had some tests for intranode performance. And that typically looked quite similar between sort of native easy and on Lumi, right?
Yes, I actually
So was
added
this
this
intranode
this was a
or,
summary graph for everything, and this is the internode graph
but is that between nodes or within a node?
within the node.
Okay. So also there
Yeah.
you still saw this latency impact, but not for Well, it was for very specific message sizes, I think, right? If I remember
Yeah,
correctly.
just the small message
Yeah.
sizes. Other than that, it comes to parity.
And that is something we haven't 100% figured out, like why this is worse with the easy build versus the native one. Okay. Any questions,
It's a
discussion?
totally different MPI implementation, so it's not that special. MPG and OpenMPI do in-node memory transfers completely differently.
Okay, yeah.
This is in fact the root of the issues that you have with OpenMPI on Lumi.
You have, sorry?
That's the root of all the issues that you have with OpenMPI on Lumi. The fact that shared memory transfers are done completely differently.
Mm.
Also, you should distinguish between GPU to GPU using what NVIDIA calls GPU direct functionality and CPU to CPU. If you do bandwidth tests and latency tests and so on.
Yes, I think
in the GPU-aware MPI, you may have totally different results, but then I guess with OpenMPI, you cannot properly do GPU-aware MPI unless you do a setup with libfabric and the LinkX provider.
Yeah. I think you tried that, no? Didn't you?
It's non-trivial. We have some success with it, but some doubts remain about the stability.
But so, I mean, within a node, this is kind of specific to how you do this on the Lumi system, right? So, I mean, intranode, it's not such a special node, right? It's not any different than an AMD node would be in another system, I suppose, right? The slingshot interconnect is the special part, basically. But it's still your vendor MPI that is more efficient also for the intranode.
Your vendor MPI may use different mechanisms to do so.
Yeah.
And in fact, Cray MPIC may do it differently from regular MPIC.
Yeah.
With the whole GTL thing, though the GTL thing is not only for performance, they did that library also to have a single MPI binary which is compatible with the various GPUs by just loading a different GTL or linking in a different GTL. But then if you want to see whether it's the ROCm version, there is a ROCm 6.4 on Lumi. In the 25.09 toolchain, we use ROCm 6.4 because those compilers are actually built for ROCm 6.4 and the Cray compiler internally uses components from ROCm 6.4. So we didn't even try to run that on 6.3, but it's not a standard ROCm module because we can have only one /opt/ROCm. It's one that we built ourselves. Also with the driver compatibility, I know AMD promised plus or minus 1 year. They haven't really delivered yet.
So in practice, you see
maybe in their very last driver, but the future will have to show. The first driver that is compatible with 4 backward ROCm versions. We still have to see whether it will be compatible with 4 forward ROCm versions. But otherwise, this has just been promises so far.
I didn't have a look at the 6.4, but it would be actually interesting to use that ROCm version and rerun the experiments again.
It could also just be compiler options.
And I guess with that one, you don't have a native build yet of things like GROMAX, or do you?
For GROMAX, we've got plenty of easy configs ourselves, but we're relatively conservative in the compiler options.
Mm-hmm.
And then for GROMAX, for GPU, you have the SYCL version and you have the HIP version.
Yes. Yeah, so that's one of the first things that we did.
Slightly more complete, I believe. The HIP version seems to be quite performant for certain computations.
Yeah, maybe you can comment on this, usual.
And then there's also the whole thing with the 2 different FFT libraries that where one is better for some cases and the other one is better for other cases. I don't know it by heart. I haven't done that GROMAX installation on Lumi, but it's very tricky.
Yeah. So for the HIP and SYCL versions, Firstly, we tried to build GROMACS with just using the simple HIP compiler, but for version 2025.1, the not all the offloadings can be done on GPU. So we actually saw how it was done on Lumi, and then we realized, oh, it is built with SYCL.
Yeah,
So
for
we
version
did,
2025, you need to use SYCL.
yes. So we built adaptive CPP as well in EESSI and used that to build GROMACS again. And we were able to get all the measurements in this presentation are actually for GROMACS SYCL. And if I'm not wrong, it uses Vulkan FFT, correct? VKFFT.
VKFFT, yeah. There is
Yes.
another one also, and which one is best depends on the use case, but I don't know by heart.
Mhm.
I would have to read our own documentation.
Any
All right.
more
Any other
questions?
points for discussion, questions, remarks?
Well, maybe just to mention that, like the work that I did on Lumi with the OpenMPI build, and that with supporting Slingshot. So I took what Kurt had done and I updated it for what was released at the time. And Internode, I got similar performance to what you see on Lumi, and then the intranode, you have the same effect, right? Just because of the way in memory stuff is done. But internode was this similar performance. Internal, yeah, internal. And that was, and I was able to inject that. So I was able to use all the stuff that ships in easy but that's just CPU based, right? So it doesn't fully meet your needs here, but it did work. So you can imagine stitching these two things together. If you stitch my recipe that enables Slingshot with your stuff, then it will be possible to do this. And I actually plan to do this in the future.
Yes, with the work you shared, I actually saw, and at some point, due to the time constraints, I didn't fully continue with it because it was CPU to CPU. But that would be a nice thing to tackle. Do you think there might be some complications related to ROCm specifically?
I would suspect there'll be complications the same that there are complications for us right now in with CUDA. So once you do an injection with the ROCm enabled MPI, you're making a choice, right, about which ROCm you're using, and then you run into problems potentially, right? So you need them to kind of match. You need what you're using, what you're injecting to match with what you're trying to use. So then you'll need a different version of the you need a different MPI injection depending on the ROCm version. But that's feasible. I mean, it's feasible to do that. It's just manual work as opposed
So
to
basically,
something
then your OpenMPI ABI becomes specific for the ROCm version that you built with, right?
At least that's what we're seeing with NVIDIA.
It's just that it also links to the ROCm library, and if you mix ROCm 6 and 7, that's going to be problematic.
Yeah, exactly.
And that's the whole thing with your ABI. Your ABI may be fixed, but you can have libc problems also if you try to inject the library. We've run into that also on Lumi, that the Lumi MPI expected a newer libc than was in a container, for instance, or just the other way around.
Yeah.
So ABI compatibility is nice on paper, but if the other system components differ, like ROCm or like libc, you still don't necessarily have ABI compatibility.
Mm-hmm.
But we can have it.
It
So
just means that it can, in principle, link those two libraries, but it doesn't say anything about the further dependencies of your code on one hand and the MPI library on the other hand. The whole ABI talk does not solve that issue.
But for the way we're approaching it, we can address it. So at least on the CUDA or the ROCm side, we have an approach to allow us to do this, but it means more work for the site, right? It means a bit more work because then you need multiple recipes, depending on what you want to support. Like, especially if you've only got a window of a year with ROCm, how many versions are we going to be shipping in EESSI in that window? I don't know.
But then it's not only that window, it's the fact that different clusters may have different, because they are in different driver versions, different compatibility constraints.
Yeah, for that we're relying on the module system to pick to check that and then verify it. We do that for CUDA already for NVIDIA drivers. We query the drivers and then we know what will work and what won't.
So basically, we then just report on a module load to the user. This thing is not going to work on your system because it's not compatible with your driver version, right? So the module is there, but it will inform you that it's incompatible with your driver version. Which doesn't make it work, but at least, it's informative.
Yeah, and then the thing is with ROCm, sometimes software with the 2 new versions still appears to work. On the last hackathon, one team actually managed to run with an experimental ROCm version, which is newer than 7.2, even though our driver on paper only goes to 7.0. But that doesn't mean that everything 7.1 or 7.2 will work, of course. The program just may not have hit any incompatible functionality.
Yeah, you might, if
And
you
in fact, the
install
way the
something new,
HMPI
then
that was a setup made by AMD, HPE, and HLRS was even a mix of ROCm 6 and ROCm 7 libraries. So the GTL was still getting a ROCm 6 library so that they could use Cray-Ampig. I don't know how they did it. It's very tricky, but we will.
I've seen similar stuff for the CUDA compatibility libraries. There's compatibilities that they say, but in practice you can usually go beyond that. But then it depends, right? Because it's like you
Yeah, we
say,
have had
you hit a
things
code
fail in
path
the
where it
past.
breaks.
Yeah, we have, especially in the 5 days, we have had things fail very quickly also. Anyway, one of the next weeks, the next Lumi should be announced.
At ISE, probably. Yeah.
At first, the plan was to do it before ISC to not be in all the noise of ISC, but EuroHPC doesn't seem to have its stuff together unless something follows this week. Or they may have changed mind.
Before we go to informal, we should close the recording.
Any final questions for the formal part? No. Recording's already closed. Richard was proactive.
Then just before stopping the recording, maybe we can go to the final slide. So next week we will be revisiting the EasyBot. It was covered pretty well in the webinar sessions. So if anyone would go over the webinar sessions and have questions for that, maybe we can then discuss them next week. I will stop the recording for now so that we can continue more informal conversation.